Okay, guys, I'm going to go ahead and share my screen again. Okay, so as I said, today we are going to be going over free body diagrams in more detail. Remember, we introduced free body diagrams before Thanksgiving break. So we're currently in 8th period, okay. And the third 6 weeks folder has already been posted in Schoology. So today begins a new 6-week period. Our final 6 weeks of the semester. Today is December the 1st, and it is a Tuesday. Okay, so the goal for today is to talk about forces. We're going to conceptualize free body diagrams, and then we're going to do a few of these problems on this worksheet as a class together. And then as soon as you guys get done with the worksheet, you're going to take a picture of it and upload it into Schoology. So everyone, please be sure that you have paper and pen. For those of you guys who are just now coming in, please be sure that you have paper and pen to do this assignment. So there are 12 of these problems. So 12 of these problems on this PDF file. The first 6 we're going to work as a class. And again, it's your responsibility to turn in all 12 when you get done with this. So you're going to take a picture of it, and you're going to upload everything into the submission box here. It says Understanding Forces Conceptually Submission. Okay, and once you upload it and I check it, that will count as your credit for today. Okay, so that's the plan on today. Now, before we go over this worksheet, I want to go over a PowerPoint with you all first, just to be sure all the concepts are solidified. Because it's very important that you guys are able to look at a free body diagram and be able to express what's happening in that particular situation. So it's important that you be able to understand the physics. Okay, and we're going to look at several real-world examples in class today. Okay, so let me go ahead and open up this PowerPoint. Okay, let me share my screen. Again, guys, you're going to need paper and pen today, because as soon as we get done with the PowerPoint and as soon as we get done looking over these few video clips that I have, we're going to go ahead and get started on the assignment together. Okay. Now, so before Thanksgiving break, I told you guys what a force diagram was, or a free body diagram. It's nothing more but a diagram that lists all the forces acting on your it lists all the forces acting on your object, and it shows you their relative magnitudes. So, for example, imagine that we have a physics textbook here sitting on the table. Okay, if we look at this physics textbook, we see that there are 2 forces acting on it. There's a gravitational force pulling downward, and then there's a normal force of the surface pushing up on the physics textbook. And both those forces are balanced. Now, guys, your goal for today is to be able to look at any free body diagram and be able to tell me what's happening in that particular situation, or in that it's your responsibility to be able to tell me what is happening on that picture. Okay, so for instance, suppose that the gravitational force here is -5 newtons pointed downward, and the normal force is +5 newtons pointed upward. Okay, so in this case right here, if the forces are balanced, then Newton's first law holds. Remember what Newton's first law says: in the absence of unbalanced forces, then an object at rest will remain at rest. So in this case right here, the physics textbook, it's at rest as it's sitting on this table, and it's going to stay at rest. So that's super easy there. We can easily look at that free body diagram, and we can easily see what is happening for this particular situation. And a similar thing for something like this here. What if I have a physics textbook sitting on a table, and imagine 2 people are pulling at the physics text, or 2 people are pulling on the physics textbook. One person is pulling with 15 newtons of force to the left, and the other person is pulling with +15 newtons of force to the right. So it should be obvious to you all that because both these forces are the same, we have a situation here in which the forces are balanced, which means this object will just remain at rest. Okay, super easy here. But what if I have something like this? What if I have a situation like this where I have a physics textbook sitting on a table and I have someone pulling with 15 newtons of force in this direction, and I have another person pulling with 3 newtons of force in that direction? So here we have a situation in which the forces are unbalanced. So because the forces are unbalanced, here we're clearly going to have acceleration. So the book will speed up. To be specific, it's going to speed up in the negative direction. And of course, and guys, just briefly reviewing what we talked about before the Thanksgiving break. If you know the mass of this book here, so let's say, I'm going to throw out a value here. Let's say the mass of this book was 4 kilograms. If you know the mass of this book here, you can easily calculate the acceleration of the book. And you guys should know how to do that. Acceleration, in order to calculate acceleration, we will need to use Newton's second law, which says that the sum of all the forces is equal to mass times acceleration. Now, remember, guys, I told you guys last time that this symbol here, it looks like a weird-looking E. That's the Greek symbol sigma, and it stands for sum. Basically, what that means is you add up all the forces acting on your object, and that equals to mass times acceleration of your object. So if I rearrange this equation here to solve for acceleration, in this case, acceleration is the sum of my forces divided by my object's mass. And of course, can someone tell me what are the sum of the forces here acting on this book? Anyone? If you add up those forces, what do you get? Yes, thank you, Nayeli. It will be negative 12 newtons. Exactly. And if the mass is 4 kilograms, negative 12 divided by 4 gives me an acceleration of 3 meters per second squared. Okay. So again, this is just reviewing what we talked about before the Thanksgiving break. How to calculate acceleration if you know the magnitude of the force and the magnitude of the mass. Okay. So let's move on. Okay. So let's look at other situations here and be able to interpret what's going on. So imagine that we have a hockey puck, and a hockey puck is sliding across the surface of this chunk of ice. Okay. Now, guys, remember there's very little friction on ice. So imagine that this hockey puck is in motion and it's moving. And so there's 2 forces acting on the hockey puck. There's gravity pulling downward, and there's the normal force of the surface pushing up on it. And those 2 forces are balanced. Well, remember what Newton's first law says. Newton's first law says that anytime you have unbalanced forces, well, anytime you do not have unbalanced forces acting on your object, then the object remains in motion. So an object in motion stays in motion at a constant velocity. So, guys, as long as this hockey puck is sliding across this ice, and these are the only 2 forces acting on it, then the hockey puck would just keep moving at a constant speed forever and ever and ever, unless another force decides to act on it. Okay. Now, imagine at the exact moment that this hockey puck is sliding across this ice, someone comes along and decides to kick the hockey puck. At that moment, we now have an unbalanced force acting on the hockey puck. So since we have an unbalanced force here, this hockey puck will clearly accelerate. It's going to speed up in this direction. Okay, so just something to keep in mind. If there are no unbalanced forces, then your object remains at a constant velocity, assuming it's already in motion. However, if there is an unbalanced force acting on your object, then your object begins to speed up or accelerate. Or it can also decelerate depending on the object's motion relative to the force. Okay, so let's look at some more examples. Okay. So, guys, let us imagine here that I have a kid here, and this kid is throwing a beach ball. Okay, so again, just pretend in your mind that this beach ball has been released from this kid's hands, and it's flying in this direction. It's flying to the left. Now, imagine at the exact moment the beach ball has been released, a wind begins to blow against the beach ball. So, guys, in that moment, what's going to happen to the beach ball? What do you think is going to happen? Is it going to speed up or slow down? Like right at the exact moment that the wind blows against it, at that exact moment, what's going to happen? Exactly, it's going to slow down. Yeah, it's going to slow down because the force is acting opposite the direction of motion. Okay. But what if we had something like this? What if we had a beach ball being thrown into the air, and at the exact moment that the beach ball comes out of the boy's hands, a wind blows in this direction? Okay. Now, in this particular case right here, so right at the exact moment that the wind blows against the beach ball is going to do what? It's going to speed up. Exactly. Thank you, Amaya. It's going to speed up. So here's the important point that I want you guys to know, because this is going to be important when we get to our worksheet. If the force acts opposite the direction of motion, the object is said to be slowing down. If the force acts in this, if the force acts in the same direction of motion, then the object is said to be speeding up. Okay, so everybody got that? I'm gonna say that again. If the force acting on the object acts opposite the direction of motion, the object is slowing down. If the force acting on the object is acting in the same direction of motion, then the object will be speeding up. Okay, so that's common sense. Hopefully, everybody got that. Now, let's talk about more complicated situations in which we have more than one force acting on our object. Okay, so in that situation right there, we were only dealing with one force. But what about if we had more than one force? Well, in order to explain these situations, I'm going to show you guys a video clip. Okay. Now, I want to show you guys a video clip of me going skydiving. Okay. About 2 years ago, I decided to go skydiving for the first time. So yes, I jumped out of an airplane from 14,000 feet in the air. Okay. So we're going to watch this video. We're going to watch the video clip first of me skydiving, and then we're going to go back and we're going to analyze the physics. Okay. We're going to look at several free body diagrams to analyze the physics of my motion in various situations. Okay, but first we're going to watch the clip. So let me... Okay.
Alrighty, Tony. How we doing today, my man?
I'm good.
Hey, I'm Nathan.
Hey.
Pleasure to meet you. Why don't we take just a wee little bit of time, explain to the friends and family, what are you doing out here today at Spaceland San Marcos?
Hey guys, this is my first time going skydiving. Letting y'all know I am afraid of heights, but that's okay.
That's all right. So am I, man.
If I can do it, y'all can do it.
That's right. So I see you're wearing an altimeter.
Yep.
So what are you doing at 6,000 feet on the way back down?
Okay, 6,000 feet. We're going to get ready to pull the parachute.
That's right.
Reach out, touch the orange ball, pull it.
That's right, man. You're going to save your own life today. You don't need cotton back there to do it, but guess what? You got cotton, the fabric of your life back there to save your life.
There he is.
So he'll take care of you. So anything you want to say before we go do this today?
Y'all pray for me.
Get in here, buddy. Get in here, buddy. Get your boy in here. How about a snapshot of the two of you? Yeah.
Got me into it, mama.
Yeah. Right. It's your fault. It's your fault. It's all right. Let's have some fun. We'll see you. Just have a good time. Good luck, everybody.
I got a little fast forward to my.
All righty, Corey. Here we are. 6,000 view out the window. Yeah, man. We're going to take you 14,500 feet high in the sky. You ready to do this?
Hey, I'm going to do this.
Yes, we are going to do this. Hey, what are you doing at 6,000 feet on the way back down? That's right, man. You're going to save your life. Anything you want to say before we go have a little bit of fun and go do this today? That's right here at Spaceland San Marcos, baby. Let's have some fun. I'll see you right outside. How about you, bud?
I'm excited.
Oh, yeah.
I gotta go rich to see what it looks like.
All right, let's have some fun, guys. We'll see you outside. Alrighty, my man. Here we are back safe and sound on the ground. What do you got to say about that? Tell all the people at home at TV Land.
Great. I didn't know I was going to get so exhausted.
But,
I couldn't feel my hands for a while, but I'm cool. I'm good. I'm back to ground in one piece. Mom, I'm okay.
Is this like a roller coaster video? Am I gonna make money?
Good or what? Right on. Well, you know what? Thank you so much for taking me with. I had a great time. Thanks for choosing Spaceland San Marcos. How about you guys get together? Big thumbs up.
Terminal velocity, baby!
Yeah, baby! Right on. Welcome to the...
All right, guys. So that was my skydiving experience. How many guys think you guys want to? How many of y'all think you all want to try that when you turn 18?
Me.
All right. Hey guys, I highly recommend it. It's an incredible experience. But of course, guys, you have to wait. You have to wait until you're 18 because you have to sign a release form. Just in case something happens to you, your family won't sue the company. So, but it's a lot of fun, and it's not as bad as you think. It's really not. In fact, statistically, guys, you're safer than you are well, you're safe for skydiving than you are in a car, because statistically, more people get killed in a car crash than they do skydiving. So it's a pretty safe sport statistically. Um, but yeah, it's a lot of fun. I would definitely recommend y'all try that out when y'all when y'all are of age. Okay. Now, one of the things I want to say here. Okay, so let's go back and let us look at this video here and let us analyze the physics here. Okay. Now, let me turn off the sound. Okay. So the moment I jumped out of the airplane, can someone tell me what was the dominant force acting on me right at the exact moment that I jumped? The dominant force was obviously what? Exactly. Thank you, Nayeli. Gravity. Uh, uh, Gravity is the dominant force acting on me. So obviously, if gravity is the dominant force acting on me, then I'm going to be speeding up while moving downward. I'm going to be speeding up in the negative direction. And of course, we all know the rate of my acceleration. My acceleration is 9.8, right at the exact moment that I jump. But guys, as I fall faster and faster and faster, another force begins to act on me as well. And of course, the more I fall, and the faster I fall, the stronger that force gets. Does anybody know what that other force is that is acting on me? What am I slamming up against? Anyone?
Air resistance.
Thank you, Jaden. Air resistance is exactly what I'm looking for. Air resistance. So air resistance is also acting on me. Now, guys, it turns out that the faster and faster I fall, air resistance gets stronger and stronger and stronger. Eventually, air resistance gets to the point to where air resistance matches the force of gravity. Okay, so the magnitude of this force becomes the same as the gravitational force. Guys, at the exact point that these two forces are in balance, me and this guy here, we're falling at a constant velocity. We're falling at a constant velocity because, remember, Newton's first law holds that an object in motion stays in motion at a constant speed. Now, guys, this point right here where air resistance matches gravity, physicists call that terminal velocity. So here I have reached terminal velocity. And guys, at this point here, you can't even feel the fall. It's like you're just floating. Like, you can't feel the fall. This is why I say skydiving is not that bad. In fact, the drop down a roller coaster feels a lot worse than the feel here. You can't even feel the fall because you're just cruising along at a constant velocity. Okay, so I'm falling and I'm falling and I'm falling, and then at a certain point I'm going to pull my parachute. Can someone tell me, at the moment that I pull my parachute, which one of these forces becomes bigger? Anyone? When I open up my parachute, guys, which of these forces become bigger? Anyone know? Air, exactly. Yeah. So air resistance becomes bigger. And guys, hopefully that makes sense why that is. Because, guys, a parachute has a large surface area. Since a parachute has a large surface area, that large surface area gathers more air as it falls. So air resistance becomes bigger than gravity. Okay. So let me go ahead and show that. So this force of air becomes larger than gravity. So in other words, air resistance becomes the dominant force. So guys, at the exact moment that air resistance becomes larger than gravity, what happens to my motion? Am I going to be speeding up or slowing down at that point? That should be obvious, guys. I'm going to be doing what?
Slowing down.
Slowing down. Exactly. And guys, it should be obvious that I'm going to be slowing down because, guys, watch what happens right at the exact moment that the parachute is released. Notice how the cameraman gets out ahead of me, because obviously at that point I'm moving slower than him. I'm slowing down. So at that point, I began slowing down because notice I'm moving in the opposite direction of the dominant force. Okay, so because I'm moving opposite direction of the dominant force, I'm going to be slowing down. So guys, as a general rule, guys, anytime you have more than one force acting on your object, if the object is moving opposite direction of the dominant force, the object is always slowing down. If the object is moving in the same direction as the dominant force, then the object is always speeding up. Okay. So hopefully that principle makes sense. Let's watch one more video clip so that I can be sure that these concepts are solidified in your brain before we actually do the assignment together. Okay. In this next video clip here, and this is a shorter video clip here, we're going to watch this young lady. Her name is Lexi. We're gonna watch her bungee jumping. Okay. So in this clip, we see Lexi bungee jumping. Okay. Now, at this point that she falls, obviously the dominant force acting on her is gravity. So she's accelerating downward. And of course, she's connected to a rope. So right at the moment that rope tightens, we've introduced another force there. Now, as she falls, she's going to land into the river below, but she's not going to fully go inside the river because of the rope that she's connected to. So she's going to fall, and then she's going to come back up. Okay. So now that we watched this whole clip here, let us go back to the beginning and discuss what's happening here in terms of our forces. Okay. So once again, I said right at this point that she's falling, the dominant force acting on her is gravity. So if the dominant force acting on her is gravity, okay, she's clearly going to be speeding up. To be specific, she's speeding up while moving in the negative direction. So she's accelerating at a rate of 9.8 meters per second squared here. And of course, the more she falls, the more we introduce other forces. So obviously there's some air resistance, but mainly there's another force that acts on her, and that is the force from this rope. And guys, anytime you have a rope or string, the force that results from that is what is known as the tension force. So I'm going to draw another arrow here to show the force of tension. So, and as the rope tightens, guys, tension is a lot larger than gravity. So at this moment right here, as she falls, she starts to slow down. And you know she's slowing down because she doesn't fully go into the water. She slows down, briefly comes to a stop, and then she begins moving back up. And here, in this case right here, guys, what's happening is she's moving up. So in this situation right here, if she's moving in the direction of the dominant force, will she be speeding up or slowing down? What do y'all think? Anyway. Thank you, Jaden. You're right. She's speeding up. So here's the point that I want you guys to see. I want you guys to notice that sometimes a single free body diagram could explain more than one situation. It could explain two situations. So here, we could say one or two things could be happening. Lexi could be slowing down while moving in the negative direction, or she could be speeding up while moving in the positive direction. Okay. Does everybody see that? Because when she's going down, she's going in the opposite direction of the dominant force. When she's moving up, she's moving in the same direction as the dominant force. So again, sometimes a free body diagram, a single free body diagram, a single force diagram can explain more than one situation. As we see here, here Lexi is either slowing down in the negative direction, or she could be speeding up in the positive direction. Okay. So hopefully everybody got that. So again, as long as you guys understand that the object is slowing down if it moves opposite the dominant force, and is speeding up if it moves in the same direction as the dominant force, you guys should be you guys should have a pretty good understanding for this assignment that we're about to do. Okay, so now is the time where you guys need to pull out your paper and pen. So we're going to work on the first 6 together, and then I'm going to let you guys go so you can do the remainder on your own. Okay, so there are 12 problems, guys, and you all are responsible for turning in all 12. You do not have to draw the pictures. Only thing you have to do is write out the answers, and then you're going to take a picture of it and then upload it into Schoology. Okay. Now, guys, whenever we're working on this assignment, just remember one thing that I told you guys, that any force that's pointed up, you want to call that force positive. Any force that's pointed down, you want to call that force negative. Any force that's pointed to the right, you want to call positive, and any force that's acting to the left, you want to call negative. Okay, so just something to keep in mind. Okay. All right, so the instructions say below, describe all the possible situations the free body diagram could be depicting. Okay, so I'm going to go over a few examples with you guys just so you guys get an idea of what I'm looking for. Okay, let's start off with number 1. Number 1 says this object is sitting on a table. Okay, so this is actually an easy one here. So it's sitting on a table, and notice how we have balanced forces acting on our object. Okay, so now, guys, in every last one of these situations, I want you guys to tell me what is the sign of the velocity, and I also want you guys to tell me the sum of the forces. So the velocity could either be positive or negative, or there could be no velocity at all. So here, if we have an object that's just sitting on a table, since it's just sitting there, that means its initial velocity is just 0. Okay, because it's not moving, it's just sitting there. Okay, and guys, be writing down what I'm writing in red. So the next thing I want you guys to tell me, the sum of the forces. Okay. So in this particular case right here, we have a positive 2 and we have a negative 2. So the sum of my forces here is just 0 newtons. Okay. So this situation is easy here. If our object is just sitting here and it's at rest, and there are no unbalanced forces acting on our object, the Newton's first law says that an object at rest will want to stay at rest. So this free body diagram here is just showing us an object remaining at rest. So that's number 1. Number 1 is super easy. So that's what you guys put for number 1. Super easy. Everybody got that? All right, guys, I'm going to move on to number 3. I'm going to come back to number 2. Number 2 is a little bit more complicated. I'm going to come back to that one. You don't necessarily have to have these in any particular order as long as you have all 12. But let's move on to number 3. We're going to come back to number 2 in a moment. Okay. So number 3 says we have an object, and this object is in motion to the left. And of course, this diagram here shows us the forces acting on the object. Okay. So first thing, we need to figure out, what is this object's velocity? Is it positive or negative or 0? Well, if the object is moving to the left, you clearly know that it starts off moving in the negative direction. So it begins with a negative velocity. Okay. So now let us figure out the sum of the forces. Okay. So so here I have a positive 3, here I have a negative 3. So those two forces cancel each other out when I add those, because they add up to 0. And then here I have a negative 7 and a positive 3. When I combine those, I get negative 4 newtons. Okay. Now, someone tell me, just by looking at this free body diagram, if this object is moving to the left, what do you guys think? Will this object be speeding up or slowing down? What do y'all think? Anyone? Thank you, Jaden. Exactly right. Speeding up. To be specific, it's going to be speeding up while moving in the negative direction. So guys, everything that I have there in red, that should be your answer for number 3. So I'm gonna let you guys write that down. So the object is going to be speeding up because it's moving in the direction of the dominant force. So this object is speeding up while moving in the negative direction. Do y'all got that? Does that make sense? Oh, and guys, here's another way, another easy way to know whether or not an object is speeding up or slowing down. If you guys look at these two signs here, if the signs are the same, then the object is always speeding up. If the signs are different, then the object is always slowing down. So, for example, this is the negative and this is the negative. Since both those signs are negative, we know that this object is speeding up. If this sign was negative and the other sign was positive, then that would be slowing down because you have different signs. Okay. All right, let's move on. Guys, let's look at number 4. Okay, so number 4 says this object is in motion to the right. So if it's in motion to the right, it obviously means it has a positive velocity. So it starts off moving in the positive direction. Okay. Now, what are the sum of the forces here acting on my object? Well, if you notice, the forces here are balanced. Positive 4 combined with negative 4 gives me 0 newtons. So here, guys, Newton's first law holds. Newton's first law says that since the object is in motion, and it's already in motion, then it's going to stay in motion at a constant velocity. Okay, so what you will write here, this object is moving at a constant velocity in the positive direction. And you know it's moving in the positive direction because it's moving toward the right. Okay. So that is number 4. Really easy. Again, anytime you have balanced forces and your object is already in motion, then it's going to stay in motion at a constant speed. In other words, a constant velocity. Y'all got that? All right, let us move on to number 5. Again, but like I said, we're just focusing on the first 6 in class together. So number 5 says we have an object that is moving down. Okay, so we know it's moving down, and here are the forces acting on it, or the magnitude of the forces acting on it. So if it's moving downward, guys, that immediately tells you the object's moving in the negative direction. There's a negative velocity. Now, figure out the sum of the forces. Okay, so the sum of the forces here, if I have a positive 6 and a negative 2, combined, that gives me positive 4 newtons. Okay. So guys, what's happening here, number 5? Are we speeding up or slowing down? Yes, sir. Thank you, Ian. We're slowing down while moving in the negative direction. So guys, on number 5, everything in red, that's what you should have. The object is slowing down while moving in the negative direction. And that makes sense because the object is moving opposite the direction of the dominant force acting on it. Okay. So it's slowing down. Okay. Another way of thinking about that, since this sign is negative and this sign is positive, since those signs are different, we know the object is said to be slowing down. Does that make sense? All right, guys, let us go back up here to number 2. I want to look at number 2 now. Okay, on number 2, so again, the question says, describe all the possible situations the free body diagram could be depicting. On number 2, we're told this object is moving vertically. Okay. Guys, you guys know what vertically means. So an object moving vertically could mean one or two things. It could either be moving up or it could be moving down. Okay. So guys, in this situation right here, we're going to have two possible scenarios. And we want to figure out what's happening, well, what would be happening to this object if it was moving up, and also what would be happening to this object if it was moving down, considering these are the forces acting on it. Okay, so here we're going to have two answers. So we need to consider two scenarios. Vertically means it can be moving up or it can be moving down. Okay, so now on number 2, if the object is moving up, that means it has a positive velocity. If it was moving downward, that means it would have a negative velocity. Okay. So what are the sum of the forces here? Can someone tell me what are the sum of the forces acting on number 2? So number 2, if you combine, yes, thank you, Isaiah. Thank you, Jaden. And it's -3 newtons. Right. So -3 newtons. So here's what this means, guys. This means here what we see here. So if our object is moving up, then the object will be slowing down. So this object could be slowing down while moving in the positive direction. Or it could be speeding up while moving in the negative direction. So guys, that is what you should have for number 2. Number 2, you're going to have two possible answers. Anytime you see that an object moving vertically, that means it could either moving up or moving downward. So you need to figure out what's happening in both those directions. In this case, if it's moving up, it'll be slowing down. If it's moving down, it'll be speeding up. So it could be this slowing down. Again, it could either be slowing down in the positive direction, or it could be speeding up in the negative direction. Here the signs are different. Here the signs are the same. Here the object is moving opposite the direction of the dominant force. Here the object is moving in the same direction as the dominant force. So here, one free body diagram can explain two situations, just like what we saw when we watched the skydiving. I mean, not the skydiving, but the bungee jumping video. Also, guys, I'm gonna say this: when you guys move to the back here, if you look at number 8 here, number 8 is similar to number 2 in that you could have two possible responses, because we see the objects moving horizontally. Remember, horizontally means the object could either be moving to the left or moving to the right. Okay, so if it doesn't tell you definitively where the object is moving, you can have more than one response. All right, guys, let us look at this last one as a class. So let's look at number 6. Number 6 says this object is in motion to the left. Okay, so since this object is in motion to the left, it begins with a negative velocity. Okay. And let us look at the sum of the forces. -3 combined with the +3 gives me 0 newtons. Again, so here's a situation here where Newton's first law applies. Because we don't have any unbalanced forces here, then the object in motion should stay in motion at a constant velocity. So this object is moving at a constant velocity in the negative direction. Okay. Y'all got that? Any questions? Any questions? So remember, it's your responsibility to do the rest by yourselves. And then you're going to take a picture of this and you're going to upload 1 through 12. And then that will give you your credit for today. Okay. All right, guys. I thank everyone for participating in the lesson for today. Remember, I'm going to keep the Zoom call open up to 3:20 just in case you guys have any questions for me. But if you guys do not have any immediate questions for me at the moment, you guys are free to go. Peace out. Bye, Nia. Have a good one, okay? See you later.